This video will be part 3 of Lewis structures and will be the final video of chapter 6 and the final video of Lewis structures, obviously. I will go over the exceptions to the octet rule. There are Lewis structures that violate the octet rule. Now remember, the octet rule states that atoms like to have 8 valence electrons to be like the noble gas. Now the most obvious exception is helium. Helium likes 2. Most noble gases like 8 valence electrons. Helium is happy with 2. So there is that exception that we'll talk about. But there are other exceptions where atoms will sometimes actually be happy with more than 8. And the reasons why are beyond the scope of this video and this course. But we will explain which elements do violate that rule and when to use that exception. So, elements that do not have an outer octet of an electron, they have more or less than 8. That is the definition of the ones that are exceptions. Now, there are electron poor atoms. That would be like hydrogen, helium, boron, and aluminum. They're happy having less than 8. All of these atoms are fine with that. Then there are atoms that are happy having more than 8, which we'll talk about later. But right now, let's do an example of an electron poor atom. So I'd look at boron. It has, and let's hit Command P here. It has 3 valence electrons. Fluorine has 7 times 3 of them. So this comes out to 21 plus 3. So the magic number, or the number of valence electrons, is 24 for Bf3. It would be boron trifluoride. Now boron, because it has 3 valence electrons, I'd put 3 dots like this, 3 single dots, bonding electrons. It forms 3 bonds. Now fluorine likes to form 1 bond, so I'd go like this, fluorine, fluorine, and fluorine. And then remember, fluorine has the extra lone pairs of electrons to put around it, so 3 pairs on each one. Not the neatest, but should work. Now notice the boron here. After this is all done, boron only thinks that it has 2, 4, 6 electrons around it. Normally that would be a big no-no, but in the case of boron, beryllium, hydrogen, aluminum, it is okay. So you're okay with that. So make sure you remember those the atoms that are exceptions. Now beryllium has 2 valence electrons. Fluorine, 7 times 2, 14, so it adds up to 16. So then for beryllium is another one like this. It's got 1, 2 dots. Two bonding electrons, which are going to bond to a fluorine. I don't think the Lewis structure part of this is too tricky. The only thing you need to know is that beryllium is happy with 4 electrons around it. And the other exception is hydrogen. Whenever you do like hydrogen, you should have done this one on a worksheet already. Methane. Hydrogen thinks that it has 2 electrons, and it is completely okay with that. It thinks that it's like helium. It's living a good life now. So hydrogen is happy with 2, beryllium's happy with 4, boron's happy with 6. Basically just follow the same rules we've been doing, and you'll be fine on these. However, these are a little bit trickier. These are electron-rich atoms. They have more than their outer octet, more than 8. These will be any element that is phosphorus or larger. So you cannot do this if it is silicon, aluminum, nitrogen, oxygen. They do not violate the rule ever. Phosphorus or bigger elements can, and they will sometimes. That's because they have d orbital electrons that can sometimes act like valence electrons, and they can start bonding with more than just the normal like 8 rule. So you got phosphorus, sulfur, selenium, tellurium, and Sb is antimony and arsenic. Can do this. So examples, SeF6. Selenium has 6 valence electrons. Fluorine has 7 times 6. Who can do that in their head? Who knows their multiplication tables? There we go. So this adds up to 48. And even though I have been kind of lazy here, checking the magic numbers, make sure you are doing that at the end of all of your Lewis structures. Now, selenium has 6 valence electrons, so it looks like this. 1, 2. Now, there's 6 fluorines. Each fluorine forms 1 bond. So you'd pretty quickly probably go like this. Put your dots in there. And now you'd be like, okay, I'm done. This is it. All of my single dots are used up. The only problem is if you use your 1 selenium, you still have 4 fluorines to go. You've only used 2 of them. So you're like, okay, where would I put these extra fluorines? And that's where the sulfur can start using its D sublevel electrons. There are a few cases, and I will tell you when the exceptions. So on a test, you'll see this is an exception. So don't start doing this unless I give you permission. But because fluorine is super electronegative, it can start, think of it as it can start using these double dots. Normally the double dots don't do anything, but I have 4 fluorines left, and those 4 fluorines are going to start taking advantage of these double dots. So you'll actually turn these double dots into bonding electrons now. And only a few elements are capable of doing this. Like fluorine is super electronegative, so normally those double dots are not fair game, but fluorine doesn't really care. So this compound would look like this. And this is pretty sloppy, so you'd probably want to redo it. Put your fluorines in. I don't need to draw them and then put all your dots on fluorine. So if all else fails and I tell you that it's an exception, you may, in a few scenarios, start using those double dots. But don't make a habit of doing it for every atom. Like oxygen, nitrogen, they will never do this. So only phosphorus or higher, and if you absolutely need to. Same thing with like phosphorus pentaiodide. Phosphorus has 1, 2, 3, 4, 5. Well, you'd start by putting your iodines on here. I'll skip the magic number this time because I'll assume you know how to do it for now. Well, actually, let's not get lazy. 7 times 5 is 35. This adds up to 40. Okay, so I got interrupted there. I'm back. Now we've got the magic number, and we have 3 of the 5 iodines used, and then we've got to add all the dots. Don't forget that. You should do a better job than I am at being neat here. And then I've got 3 of the 5 used, so I got 2 left, and conveniently there's 1 pair left here. And I would tell you in a test or a quiz that there's an exception. Sorry, that dot shouldn't be there. So then you just strip those 2 double dots and start using them as bonding electrons. That's how I like to do this. So then this is pretty sloppy, so I would have you just redraw it with 5 lines, put your iodines in your double dots, and you'd be good to go. So that's how you do exceptions. On a test, I would not tell you if it's electron poor or electron rich. I would just say this is an exception, and that gives you permission to kind of bend the rules a little bit. You may have to use the lone pair electrons to do some bonding with, or you may end up having elements that only have 6 valence electrons or 2 valence electrons around them instead of the normal 8 that you're used to. So take that, and you should be able to finish all your Lewis structures on your worksheets, and there you go. Have fun drawing Lewis structures.